Thank you for the introduction, and I would like to thank the audience for attending the talk. I know this is the last session, and you must all be tired, but I'd like to thank you for the attendance. So, hello everyone, my name is Salma Al-Malaki, and I'm going to present our work in CareDroid framework, an adaptation framework for Android context-aware applications. This work is done in Networked and Embedded System Lab at UCLA. Computation used to be isolated in closed room, disconnected from the real-world situation in which they are used, unaware of the surrounding environment. However, computers are not isolated anymore. Taking the context of a human and what surrounds him are used into the loop of computation. For example, imagine your phone senses your stress and starts to give you advices on how to cool down, or imagine that a software engages in an activity that can distract you from the source of stress. Imagine a remote control that instantly determines who is holding it and automatically selects the smart TV preferences for that person. The need for smart devices that understand you makes the context-aware applications essential. The core of context-aware computing can be summarized into three main parts: sensing, in which mobile phones acquire the raw information about the current environment; understanding what this information means; and adapting the behavior of the mobile phone accordingly. In this work, we build a systematic support for context-aware applications that facilitates their implementation. We call it CareDroid. CareDroid is implemented as part of the Android runtime system. By pushing context monitoring and adaptation into the runtime system, CareDroid targets these challenges. The adaptation to the environmental change should happen automatically and at runtime. The adaptation should not be a burden on the user. The overhead of reading the environmental context should be small. The concept of context awareness goes back to 1994, actually, when it was first defined as a system with certain capabilities that can examine the computing environment and react to the changes in this environment. In that sense, there have been a vast amount of work in the sensing and understanding part, but most of the adaptation part was designed and implemented with a specific focus on energy-aware context adaptation or to perform context-aware OS functionalities, such as context-aware memory management or context-aware scheduling. In our work, we focus more at having a systematic support for the adaptation part of the context-aware applications. A main idea of the CareDroid can be viewed as a function adaptation. Applications normally call method f. Each method is aliased to one of other version different in implementations. For example, in this slide, you have f and it's aliased to f1, f2, f3, and so on. At runtime, the method that fits the current context replaces the original function call and is executed instead. So for this example, we have, if the location and activity have certain values, f1 will be executed instead, while f2 replaces f under certain values for temperature and battery status, and so on. Now I'm going to explain how this idea is achieved using CareDroid. The architecture is designed to satisfy the following properties. Usability. CareDroid needs to add minimal overhead on the application developer at developing time. Performance. The adaptation engine needs to add minimal execution overhead when the application is running. CareDroid is designed on three layers. The first layer is the application layer. The developer provides the function and their alternate implementations. For example, F here has three other implementations. For each function, operation range is defined in a configuration file, such as, for example, F1 can be triggered if the battery capacity is from 20% to 100%, while F2 can be triggered from 60% to 100%. So this is defined in the configuration file. The second layer is the system layer. CareDroid parses the application configuration file to discover the adaptable method and the rules of operation. The third layer is the context sensors, and this layer abstracts the various sensors in the system and exposes context information to the adaptation engine. In the following slides, I'm going to explain how each layer works in more details. So for the sensitivity configuration file, the developer assigns a sensitivity list. This sensitivity list is the list of context states for which this function implementation shall be triggered. In keeping with our goal of decreasing development complexity for context-aware application, the file is a straightforward description for the acceptable ranges of operation for each method. So for the example shown, we have two methods alias to each other. The first one is called adjust camera power aware, and the second one is called adjust camera while running. So for the first function, you have battery capacity from 0 to 25, and it can execute under different motion activity. While the second function has capacity from 20 to 100, and it can execute under different, it can execute only if the phone holder is running. As seen, there is a conflict in the ranges of operation, and here comes the use of priority for the methods. Each method is assigned to a priority that is used later to solve this conflict. The sensitive function registration part is responsible for understanding the ranges of operation of each method and for integrating it into the Android runtime system. And this is done as follows. The sensitive functions and their ranges are defined in the configuration file during the developing time. Upon compilation of the Java code, the generated Dalvik executable file, which is called DEX, contains all compiled bytecodes of method stacks on top of each other. The DEX file, along with CareDroid configuration file, are then packed together normally through the normal Android flow in the application package file, which is called the Android APK. When the APK file is installed, Android creates a new virtual machine to host the application. During this process, the Android flow extracts the DEX file and post-processes it in order to generate a fast optimized version of it called optimized DEX, the ODEX file. CareDroid intercepts this process and modifies the DEX ODEX build process in Android to add hooks for context awareness in methods. These hooks are special data structure. We call them the replacement map and the table of range identifiers. Replacement map is a collection of key value pairs defined for each sensitive function. The key of this map is a composite key that consists of a pair of class ID and method ID, extracted initially from the DEX file and updated during the installation process. The value field of the replacement map is an array whose length is equal to the number of contexts we are currently handling in CareDroid, which is the battery capacity, battery temperature, battery voltage, Wi-Fi connection, quality of the signal, signal strength, motion activity, and the GPS location. The number associated for each context comes from a table of range identifiers. The table of range identifier consists of multiple associative arrays. For each of the context sensors, CareDroid creates a corresponding associative array. It extracts all the operation ranges provided in the configuration file and then associate a uniquely generated operation range identifier, we call it the ORI, so that for each operation range, for example, here you have from 20 to 30% for the battery capacity, it is assigned to a uniquely identifier, which is 2. After creating these two special data structure, CareDroid extends the ODEX file by adding reference to the replacement map and the table of range identifiers. The second module in CareDroid is the context monitoring. While the main contribution of CareDroid is not the efficient implementation of context monitoring, it is still essential in any adaptation engine. So here, as we said, we focus on the battery state, which is the capacity, the temperature, which can be indicative for high battery load or high power consumption, voltage, which can be an indicator for the battery health, the connectivity state, the location. The developer can provide the longitude and the latitude he wants for the GPS. And we seeded our context monitoring module with previous work that has been done for mobility inference, as for running, walking, and standing still. So in order to reduce the overhead of context monitoring, we need to bypass the hardware abstraction layer, the HAL layer, and the associated sensor managers. This can be done by snooping on the interface between the hardware abstraction layer and the low-level device drivers. Indeed, this work also can be augmented or enhanced by the context monitoring system recently proposed in literature. The third module in our system is the adaptation engine. The adaptation engine is the core of CareDroid. It's where the method replacement happens at runtime. Since this is the core of CareDroid, in this section I will explain how CareDroid extends the execution phase of Android flow to automatically and transparently switch between methods. The developed application is compiled again and translated into the ODEX file. bytecode stored into the ODEX file and is interpreted at runtime using the Dalvik interpreter. Method is called using Dalvik opcode, which is called invoke virtual quick. It's shown here. The instruction call has the method ID and the class ID of the called method. This will be used as an entry to the class virtual table, and then the corresponding bytecode of the method will be executed. CareDroid intercepts this execution of the interpreter. It then checks the arguments of the invoke virtual function, invoke virtual instruction. If the method ID and the class ID corresponds to a sensitive method, then CareDroid execution flow starts to choose the best method to execute based on the current context. This is done using CareDroid decision graph along with the table of range identifiers and the replacement map we have explained previously. Since it's possible that for a given context, multiple methods are valid candidates, this leads to a conflict that needs to be resolved. This is done using CareDroid decision graph. CareDroid decision graph is a directed acyclic graph. Each level of the graph marks one sensitive context. The sensitive contexts are ordered based on their priority, and again, this priority is defined in the configuration file. Each node identifies one range identifier, marking a distinct range of operation for the corresponding context. According to the current context, there will be an active path marked here as solid gray arrows and an inactive path marked as dotted gray arrows. The final step, CareDroid compares the available active path that starts from the top level and choose the best path marked here as green, as the green arrows. CareDroid allows for two policies. The must-fit policy, in which CareDroid considers only the active path that connects the first level all the way down to the leaves of the graph. If no such path exists, then no method replacement is going to take place. On the other hand, the best fit policy considers the longest path that starts from the first level. So if a method only satisfies one rule, then it's a candidate method. Decision graph then returns the class ID and the replacement method ID for the replacing method to be executed, and this is passed to the class virtual table for the method to be executed. While the strategy of adaptation engine in CareDroid is straightforward, performing it for every individual sensitive call method would cause an unnecessary overhead. In order to decrease the overhead of the context to method resolution mechanism, CareDroid uses a resolution cache. Therefore, if a method is called multiple times within a short amount of time, for example, inside a loop, the same method implementation might be used for all these calls. So, by pushing context monitoring and adaptation into the runtime system, CareDroid eases the development of context-aware applications and increases their efficiency. In particular, case study applications implemented using CareDroid are shown to have at least 2x reduction in the lines of code, at least 10x more efficient in the execution time compared to the equivalent context-aware application that use only standard Android APIs. So if we implemented the context-aware application using Android APIs and using our CareDroid framework, then we can achieve down to 10x more efficient in execution time. So for the sake of time, I will present only one case study for CareDroid, but we have more interesting case studies presented in the paper. So here we show a context-aware camera that is built using CareDroid. So this is a camera that can change its focus and its mode, its features based on the current context. So this is a photo that's taken while the person is standing still. And this is a photo that's taken while the phone holder is walking with no context awareness is taking place. So he's walking and capturing the photo. So as you've seen, it's hazy. And while this is a photo that's taken while the phone holder is walking and using the smart camera application that was built on top of CareDroid. This table shows the reduction in the significant line of code, the SLOC, when the context-aware camera application is developed using normal Android flow compared to the proposed CareDroid, using the normal Android flow compared to the proposed CareDroid flow. So the table here shows a reduction of SLOC by more than a factor of 3x. And this is basically comes from the configuration file. So the XML file, which has all the operation ranges, actually what contributed in the numbers, that is 133, which is the overhead of the line of code compared to an application that is built with no context awareness. We further make analysis for CareDroid system in order to analyze the effect of the cache in the adaptation engine, the overhead of context monitoring module, the energy consumption and the execution time comparison between pure Java implementation using Android APIs and CareDroid. All case studies are carried over an Access4 phone running a modified system image for platform 4.2 API 17. The overhead of our system image in CareDroid is only 4.6%. This table shows a breakdown for the execution time for each part of CareDroid system. I will walk you through the important numbers that I want to focus on. So again, we provide two levels of complexity to map from context to method, a binary criteria called must fit, and a relaxed criteria called best fit. A must fit, a method is considered a valid candidate if the current context satisfies all operation ranges for all the sensitive contexts. In the second policy, which is a best fit, a method is a valid candidate if the current context satisfies at least one operation range of the sensitive contexts. The choice of the policy is determined in the configuration file. CareDroid reduces the CPU time overhead compared to the pure Java implementation by a factor of 12x on average, while adding a minimal overhead of 2.5 to 6% compared to the non-context aware case. The resolution cache leads to decreasing the decision tree time by at least an order of magnitude whenever there is no change in the operating time. Finally, with no cache, or alternatively, when a cache miss occurs, the best fit policy adds slightly more overhead compared to the must fit policy due to the complexity of the decision graph we explained. The same order of magnitude also appears in the pure Java implementation because of the added code of switching between the context and the methods. We compare the energy consumed by the same application in the four scenarios using pure Java implementation, using our two policies, and using the non-context aware scenario. For the sake of time, I will just show you that we achieve 69.33 energy saving compared to the pure Java implementation. This measurement is taken every 5 seconds from the power controller circuit of the phone, and the context is driven using snooping over the hardware abstraction layer. For the future work, as we can see, there are a lot of opportunities to enhance CareDroid. The first one is to migrate to new versions of Android that are based on Android Runtime, ART, instead of the Dalvik. Add support for more abstract context. If, for example, if the phone is augmented with other monitoring devices, you can abstract information about the stress, the fitness, smoking. Also, you can make the adaptation engine a secure aware by changing the phone behavior to hide this information. Also, we are considering adding the time of day as another context to CareDroid. Thank you, and please check the paper for other more features we support in CareDroid and other interesting case studies. Thank you.
Let's thank the speaker.